Today we're going to take a look at nonlinear graphs and then also how we can solve linear and quadratic systems. So one thing that'll really help you on the SAT is just to know what general polynomials look like. So if you have a positive leading coefficient, and if you're not sure what I mean by that, that would be like if you have a y equals, we'll say 2x squared, that graph is going to open up. If you have y equals a positive 3x to the fourth minus 7x, that graph is going to open up. Whereas if you have a negative leading coefficient, those graphs are going to open down. So these are examples of positive leading coefficients on the left. Over here, if I've got y equals, we'll say negative x to the fourth. That might look something like this down here, or y equals negative 2x squared might look like something like this over here. So negative leading coefficients are always going to open down. Even degree polynomials always have the same end behavior. So if you have an x squared, x to the fourth, x to the sixth, and so on, they're all going to open up if that leading coefficient's positive. It's just a question about what's going on in the middle of the graph. If your leading coefficient is negative and it's an x squared, x to the fourth, x to the sixth, and so on, both ends are going to point down. It's again just a matter of what's going on in the back. Or in the middle, I should say. If you have an odd degree polynomial, so if you've got an x to the first, an x to the third, an x to the fifth, and so on, if that leading coefficient is positive, think about if you have a positive 1 or x to the first power, that's a line that's increasing. You're going to see the same thing. This is an x cubed here. It has that same general end behavior. Then if you kind of increase, still same general end behavior. So it's just a matter of increasing with a positive leading coefficient, just what's happening in the middle. So we'll say positive a squared, or I'm sorry, a to the third, fifth, etc. on the left. Negative leading coefficients, so negative a to the third, negative a to the fifth, and so on, they're going to decrease just like a negative x would. So here, decreasing trend. Again, it's the same idea. It's going to decrease. It's just what's going on in the middle of the graph. So here's an example we're going to graph in factored form. If you're going to graph in factored form, remember that you should always easily be able to find your x-intercepts by setting the factors equal to 0. So we get x equals negative 3. And x equals 2. This is going to be a cubic function because you've got an x here and then you've got another x and another x because this is an x squared. So this is going to be an x cubed, which means that it's going to have this kind of general shape, and it's a positive x cubed. So it's going to increase as we go from left to right. So I can kind of guess that my graph's going to come from the negative direction and increase up this way. It's going to do something in the middle, and then it's going to be increasing again over here. And that might be enough to get you credit on the SATs or get you the right answer choice. If not, you can pick some x values and solve for y. Pick some values that are in between here. So maybe I pick x equals negative 1. So if I plug in negative 1, I get 2 times a negative 3 squared. So it's going to be 9 times 2, or 18. So at negative 1, I'm way up here at 18. So I'm just going to kind of estimate where that would be. And then maybe I pick x equals positive 1. That's going to give me 4, and then times 2 squared. So it'll be 4 times 4, or 16. So at 1, I'm up at 16. So again, just kind of estimating where I'm going to be. So this graph's going to come up and do something like this. I'm not sure exactly how it's going to look, but that should be good enough for the SATs to narrow down your answer choices. You also have rational functions, so keep in mind when you're dealing with rational functions that you can't divide by 0, so you're going to end up with what we call an asymptote, and those asymptotes are just those lines or invisible lines that your graphs can't cross. So, for example, we have our general form here, This x minus h tells us where our vertical asymptote is. You can see here a vertical asymptote at h, horizontal asymptote at k. And then once you have those asymptotes, you should have a good enough idea as to how that graph's going to look, or you can make a t-chart and plot some points. So here's an example. This is going to give us our vertical asymptote at -2. This is going to give us our horizontal asymptote at -1. And then that might be enough to graph our function. If not, we can pick some values for x and y. We can make a t-chart. Maybe I pick x equals 0. If I plug in 0, I've got -4/2, which is -2. And then -2 minus 1 is going to give me -3. So at x equals 0, y is -3. Well, now I at least know what quadrant this is going to be in. So it's going to look something like this. And then it's always in the opposite quadrant. So the other one's going to look something like this without even picking any other x values. As far as domain and range goes, our domain is all the x values. This is really all real numbers except our restriction. So for our domain, our x values, we can't cross this line here at -2, so except -2. Our range, same thing, it's all real numbers, but vertically we can't cross this line at -1. We had talked about solving linear systems by graphing and that you're going to locate the intersection point. And so you can do the same thing with higher order polynomials. If you have 3 or more equations that are graphed, make sure you find where all 3 intersect. So for example, if I had something like this parabola and a linear equation and another linear equation, I kind of missed the mark there, but we'll say all 3 intersected right here. I'll just make that a big point. That would be the solution, not this here, because only 2 of the 3 equations cross at that point. You can also solve quadratic systems using algebra. And so the way that you would do this is that these are both equal to y. So we can essentially use substitution and substitute this into the y over here and make this 2x minus 2 equals x squared minus x minus 6. Now we want to set this equal to 0 so we can see if we can factor. So I'm going to move over the 2x and the 2. I now have 0 equals x squared minus 3x minus 4. X times x to the x squared. 4 times 1 will multiply to give me 4. If I use a -4 and a +1, that'll give me that -3 in the middle. So I get x equals 4, x equals -1. If I needed to solve for y, I could. So if I needed the whole ordered pair, I would plug these in one at a time. So when x is 4, I would have 8 minus 2. That's going to give me y equals 6. If I have x equals -1, that's going to be a -2 minus 2. That'll give me y equals -4. So these are our ordered pairs. So you've got nonlinear equation graphs and linear and quadratic systems on Khan Academy for today.